and Bernstein will continue his lectures on integer factorization.
Thank you. Just as a quick recap from last time, the Q-sieve, the typical congruence combination method of factoring a big number n, finding the large prime factors of, well, any prime factors of the big number n, is writing down a bunch of congruences, numbers I times n plus I, referring to the fact that I is congruent to n plus I modulo n, looks for congruences that are y smooth, and then tries to combine them by linear algebra on the exponent vectors into a congruence of squares, where hopefully these square roots are sufficiently random that their difference is going to reveal a factor of n by a simple GCD computation. The number of congruences that you need to combine, well, you are guaranteed that if you have more vectors than components in each vector, if you have more than about y log y vectors, then certainly that's enough. Maybe that's overkill, but let's just assume enough means about y over log y vectors, about y over log y smooth congruences. And the formulas from last time about smoothness probabilities told us that if y is chosen as e to the square root of 1/2 log n log n, then it's good enough to take y to the 2 plus little o of 1 congruences. That will give more than y smooth congruences, and that will produce a factorization of n. The same basic shape of y and the same basic shape of the algorithm applies to more fancy combining congruences algorithms like the linear sieve, the quadratic sieve, the number field sieve. I'll focus on the number field sieve next time and then try to optimize it. All of them have the same flavor of y is chosen as something sub-exponential in the size of the numbers that you want to have being smooth. The numbers that you want to have being smooth become a lot smaller in those other algorithms. But today I want to focus on the question of how do we tell which of these congruences are smooth. Ignoring where the congruences come from, we just have a bunch of numbers. We have a bunch of I times n plus I, or generalizations that are smaller, and we have some number y, which is sensibly chosen as something that grows sub-exponentially in the size of those numbers. How do we figure out which of the congruences are smooth? Now, this is another situation where, of course, we can tell. There's no difficulty in solving the problem, even solving it in polynomial time in the input size, the input being all the congruences. There are y squared congruences to look at. This very simple algorithm, trial division, that'll tell you the answer in y cubed bit operations. You just take each of your congruences, each of your I times n plus i's, and try dividing by 2. If you find a 2, try dividing by 2 again, and keep going until there's no more 2's, and then try dividing by 3. Keep going until there's no more 3's, and then remove all the 5's and 7's and 11's, and you can remove all the 9's if you like. It's not going to do anything. But try dividing by all the numbers up through y, or all the primes up through y, and that will tell you whether your input is smooth. In particular, out of y squared congruences, it'll tell you, at the expense of doing divisions up to y, it'll tell you whether that number is smooth or not. It'll give you about y smooth congruences. The total time here, if they're y squared numbers, and y, or y over log y divisions per number, it's about y cubed bit operations. The whole game today is going to be reducing y cubed to something smaller, seeing how close we can get to y squared operations, which is what we would like for y squared inputs. The name of the Q-sieve, the name of the linear sieve, the quadratic sieve, the number field sieve might suggest to you the standard answer. And the picture that I was drawing last time of all the numbers divisible by 2, they're nicely spaced as every second number is divisible by 2. All the numbers divisible by 4 are nicely spaced by 4s, and same for every prime and prime power, is that you can easily write down arithmetic progressions of which i's have I times n plus I being divisible by p. If you have a particular p and you want to know which I times n plus i's are divisible by, say, 7, well, it's if I is a multiple of 7. Looking at the middle paragraph there, for any p, you just write down those are pairs of I comma p, where I is divisible by p. Well, p comma p, 2p comma p, 3p comma p. And then pairs where I plus n is divisible by p. Equally easy to write down. There's very few of them as p gets big. Once you've written down those pairs for one p, well, do the same for every p, and then sort those pairs. Traditionally, people will sieve by distribution sort, which means you just have an array indexed by I and throw your pairs I comma p into the array at position I, throw p into an array at position I. There are lots of ways to sort numbers, and I don't care about those for today. I just care about sorting being some very fast thing that you can do with all these numbers. There are not very many of these pairs. The number of these pairs is comparable to, well, it's exactly the number of factors less than or equal to y of all the numbers. And any particular number has very few factors, so there's very few pairs being written down. The total number of bit operations for sieving is, for y squared congruences, something like y squared times log y to the big O of 1. And I won't care what that power of log y is. So sieving is very fast. Again, the names of these algorithms, like the Q-sieve, might suggest to you that this is what these algorithms do, is sieve numbers. Certainly generalizations like the number field sieve still have sievable numbers where you can easily write down arithmetic progressions of i's or lattices of pairs I, j, where the congruences that you write down are divisible by any particular p. Then by sorting, you know all of the primes p dividing a particular I. Even though this is a very simple answer and the answer you might expect, it is not what record-setting factorizations actually do. What I'm going to tell you today is what record-setting factorizations actually do as compared to sieving. When I get to earlier boards, I'll explain how things are combined with sieving. The reason that people don't sieve, even though the number of operations used by sieving is ridiculously small, as small as you can imagine per number, sieving has a couple problems. And the first problem is that it doesn't work well with sublattices. Remember from last time that if you write down pairs I and n plus I, as I grows, those numbers grow. They become less likely to be smooth. Same thing for the number field sieve, even more dramatic effects for the number field sieve. The smoothness chance drops as you let your congruences grow. Well, to avoid that, you can look at congruences in sublattices by switching sublattices as often as you can, writing down instead of y squared, instead of an arithmetic progression of y squared values of I, you have, say, y squared sublattices with one I in each sublattice, and that will give you the smallest congruences that anybody knows how to find. But that means you can't sieve. Sieving requires that you look at a long arithmetic progression of i's. Sieving requires that you are trying to find the smoothness, you're trying to find small factors of values of a polynomial, consecutive values of a polynomial, where the number of consecutive values you write down is something comparable to the prime, the largest prime that you're looking at, something comparable to y. Otherwise, if you only have a few i's to look at, you could try sieving them. You could try combining the effort of trial division on those numbers, but if you only have a few i's, you're going to spend more time thinking about the primes than you are thinking about the individual numbers, and the time of just looking through your primes will be a bottleneck. In order for sieving to be efficient, you have to have an arithmetic progression of values of I fed through some polynomial like I times n plus I. Then you can sieve. That does not work well with sublattices. It does not give us the smallest I times n plus I. This is a problem we can fix. As said on the slide, you can eliminate it using remainder trees. Let me tell you how remainder trees work first. I'll tell you how product trees work. Product tree is, well, a tree of products. You're trying to multiply a bunch of numbers. Let's call them C1, C2, etc. through Cm. Maybe these are primes. Maybe they're C's might suggest these are congruences that you're trying to multiply together for reasons that will be clear in a little bit. Let's suppose that you have a batch of congruences that add up to about y bits. Now, we actually have y squared, so let's split the y squared congruences into y batches, each of which will be a batch of y bits of congruences. All right, when you have y bits of numbers, integers, I claim you can multiply them together in time about y, rather than the y squared that you might expect. If you have y little numbers, and you multiply 1 times an x, times an x, times an x, and so on, just the volume of data you've written down is quadratic in y. But no, you can compute the product in time essentially linear in y. Because you can compute the product of the first half of the numbers and the second half of the numbers recursively, and then multiply those halves together using fast multiplication. The big structure of what you write down, that's the product tree. You just form a tree where the top of the tree, the root of the tree, is the product of all the numbers, C1 times C2, etc., times Cm. And then the left subtree is a product tree of the first half of the numbers, and the right subtree is a product tree of the second half of the numbers. So each node in the tree, I have an example here, Each node in the tree is simply the product of the two numbers below it, if it's not a leaf node. This is the product tree of 23, 29. You can see in the bottom left of the product tree, 23 times 29 is 667, and that gets multiplied by 84. On the right side of the tree, 15 times 58 is 870. That gets multiplied by 19, and then the halves of the product get multiplied together to form the product of everything at the root of the tree, this number at the top, 92614, etc. All right, each level of the tree is obtained by multiplying numbers at the level below. And here I'm just going to state as an axiom that fast multiplication takes time essentially linear. If you're multiplying y bit numbers, that takes time instead of the y squared that you might think. It takes time something like y times log y, maybe times log y, depending on your model of computation. It's a very fast operation thanks to the fast Fourier transform and various ideas by Schoenhagen and Strauss. If you believe that, then, well, hey, I can sell you anything. No, fast multiplication is a standard technique, and every level of the tree has only y bits. So doing multiplications, if multiplication takes time logarithmic per bit, then the total time is the total volume of the tree times the log factor. The total volume of the tree is y times log y. So overall, it's something like y times log squared y. All right, that brings me to remainder trees, which I said will avoid the sieving problem of having to have numbers in arithmetic progression. In general, suppose you have some non-zero integer c1 through cm, and a big number, big P, which is going to be divided by c1 through cm. You do that by dividing P first by the product of the c's, and then dividing it by the product of the first half and the product of the second half, and then dividing it by product of subpieces. Well, in general, the remainder tree is just like the product tree, but for each node in the product tree, you replace it by P mod that node of the product tree. That gives you the remainder tree. Here I've written down, for instance, a remainder tree of some big number and the same 6 small numbers, 23, 29, etc. from before. You can see in the bottom left, the remainder tree has a node 46, which is big P mod 667, and then big P mod 23 is 0, big P mod 29 is 17. Each node in the remainder tree is obtained by reducing the nodes above it by division. And if you believe that division is about as fast as multiplication, computing the remainder tree is about as fast as computing the product tree. Once you have these tools, then it's very easy to see whether numbers are smooth. If you have a whole lot of numbers you want to test for smoothness, now these don't have to be in arithmetic progression. You first compute the product of the primes, multiply together all the primes less than or equal to y, and call that product big P. Incidentally, the theme for today is going to be writing down big numbers that are products of lots of little primes. But I'll show you lots of other methods of doing that. Right now, we're just going to write down by multiplication, enumerate the primes less than or equal to y, multiply them together, forming a number with about y bits, 1.4 times y bits maybe, and then compute that big number, mod all the little congruences that you want to test for smoothness using the remainder tree. And then separately, for each number, if you want to know if C sub I is smooth, then you just check if it's a divisor of P. Well, okay, maybe not quite that simple, but basically a smooth number is a divisor of the product of the primes less than or equal to y. Glossing over, all right, there's maybe little powers of the small prime, so to do it right, you should take P mod C1 or P mod Ci to the power 2 to the k, where k is just big enough to account for the maximum possible power of 2. And that's a very easy little exponentiation, mod each C1 separately. Once you know P mod C1, just square it k times mod C1, where k is very, very small. And that tells you whether C1 is smooth. Or more generally, if you want to know the smooth part of C1 and find the unfactored piece. For instance, if the unfactored piece is less than y squared, then you know it's prime. Anyway, this tells you the y smooth part of each C sub I. The total time for this, if you have a batch of y numbers or a total volume of y numbers, again, we started with y squared congruences, but chopped them into y separate batches, each of which is y bits long. The total time for this is some logarithmic factor times the volume of original data, just like sieving if you don't ask what the power of log y is. I said sieving has two problems. One of the problems I just removed, but the other problem I definitely did not. The other problem is sieving uses a ton of memory. Sieving, if you want to sieve up to, for instance, y equals, for cutting edge factorizations, people are thinking about 2 to the 40, even beyond that to 2 to the 50. If y is something like 2 to the 50, in order to sieve efficiently, you need to write down something like 2 to the 50 bytes of data. And that's pretty big. We have computers that store 2 to the 50 bytes of data, even more. The most famous one of those computers is called the internet. This has something like 2 to the 60 bytes of data. But you cannot very efficiently access those 2 to the 60 bytes of data. If you look at this real computer, the internet, it gives you very, very slow access to 2 to the 60 bytes of data. You have very fast access to maybe 2 to the 30 bytes of data. Actually, there's a whole hierarchy. If you look inside your little computer, your node of the internet, then you have very fast access to level 1 cache, a little bit of very fast memory, and then some slower memory, level 2 cache, and then some even slower storage, dynamic RAM, and then some even slower storage called disk, and then some really, really slow storage called the local network if it's actually working, and then you get, finally, the rest of the internet. And, well, it's just not reasonable to imagine that you have very fast access to the 2 to the 60 bytes of storage that your entire machine has. You have to work locally inside small pieces of your storage. And sieving doesn't do that. Sieving really needs to look at a whole lot of memory. Just like linear algebra does. I mentioned last time that linear algebra can be a bottleneck in factorization computations for exactly this reason, that linear algebra really has to use a lot of memory, but we can reduce the cost of linear algebra by scaling y down, and we can't really do that to sieving. There comes a point when you've made y so small that linear algebra is not a bottleneck, but sieving, you have to sieve so many numbers that it's just not practical anymore. All right, so real computers, you can't just assume that you have as much as y bytes of storage to work with. If you're doing tiny computations, then you don't see this, and it's perfectly reasonable to say that sieving is very, very fast if you're sieving inside, say, level 1 cache. But if you're doing a big computation, cutting-edge factorization, then you really can't sieve. You won't get cutting-edge record-setting results by sieving. So the question that will occupy me for almost the rest of the talk is, how do we avoid using a lot of memory? How do we quickly find big prime divisors of congruences without having to look at a whole bunch of congruences at the same time, without having to form a big remainder tree, without having to sieve? Let's just try looking at one or maybe a few congruences at the same time. What can we do with that? Well, we can certainly do better than trial division. And the easiest way to see this is with the row method. If, for example, you start with row sub 0 equals 0 and define each subsequent row value, I'm defining row 0, row 1, row 2, etc. Define row sub k plus 1 as row k squared plus 11. These numbers rapidly get big, but let's not worry for the moment about how big they are. I claim that every prime less than or equal to 2 to the 20th divides row 1 minus row 2 times row 2 minus row 4 times row 3 minus row 6 times etc. All those factors are negative, I guess. They're not 0, so this is not a trivial statement. I actually wrote down row 1 minus row 2 times row 2 minus row 4, etc. Computed that in my head, factored it, and found every prime less than or equal to 2 to the 20th. No. I computed that product mod each prime less than or equal to 2 to the 20th and verified that every one of them, the product came out to 0. There's also a bunch of primes bigger than 2 to the 20th. Giving a name to this product, calling it S, if you want to factor some C, if you want to find small prime divisors of some C, hopefully C is smooth, well, since S has a lot of small prime divisors, you can compute the greatest common divisor of C and S, and that'll tell you at least the factors that C has in common with S. That's a doable computation. That's something where, well, for any given C, you can compute each of the rows mod C, and then subtract them and multiply them, doing all the computations mod C. And it takes only about 2 to the 14 multiplications mod C. The total memory usage is very small as long as you're computing simultaneously. Don't store row 1, row 2, row 3, row 4, etc. Compute row 1 and then compute row 2 in a separate column, and then move from row 1 to row 2, move from row 2 to row 4, move from row 2 to row 3, move from row 4 to row 6. At each step, move from row sub 2i to row sub 2i plus 2, and move from row I to row I plus 1. As long as you double the work of computing the row subides for small I, then you don't need any storage for this. This is not really faster than trial division. You could write down just as easily S being the product of all the primes less than 2 to the 20th, and that would be about as many multiplications mod C. But this method scales better than trial division does. Suppose we take exactly the same sequence, and instead of going up to, what was it, 3,500 or so, we go up to Z. So you compute row 1 through row Z, and simultaneously row 2 through row 2Z, subtract the corresponding row K minus row 2K, multiply those all together, do all the computations mod C. Then it's something like, what, 2Z, 3Z, 4Z multiplications, mod the number C that you're trying to, the congruent C that you're trying to factor. And, well, I claim that this will detect all the primes less than or equal to y. S is going to contain all the primes less than or equal to y. When Z is only something like square root of y or square root of y log y, Z only grows as the 1/2 plus a little of 1 power of y, as opposed to trial division, which grows like 1 power of y. If you just wrote down S being, instead of this product, write down just the product of small primes, well, okay, the work for that grows as y to the 1 plus epsilon. This work grows as y to the 1/2 plus epsilon. The reason for the 1/2 is, well, if you look at the rows mod a given prime p, then, well, those are random kind of numbers mod p, and you figure if you write down square root of p random numbers mod p, then they're going to collide with some pretty good chance. And if you go up to, say, square root of p log p numbers, you're practically guaranteed they're going to collide. Once you have a collision, rho sub I mod p being rho sub j mod p, that guarantees that rho sub I plus 1 mod p is rho sub j plus 1 mod p. And continuing that to some rho k and rho k plus whatever, and then you get a whole cycle, rho k equals rho 2k, when k is any multiple of j minus I that's at least as big as I and at least as big as j. So it's perfectly reasonable to imagine that when Z is only about the square root of the biggest primes you're looking for, square root of y, times a little fudge factor, because this is all statistical, whether any given prime actually gives you a collision after only square root, or 2 square root, or 3 square root. Let's say square root of p times log p. That's a reasonable upper bound for how soon the rows are going to collide, and in other words, how soon p is going to divide s. We can try to do better. The theme for today is, again, writing down big numbers, but still fairly easy to compute numbers that are magically products of lots and lots of little primes. And the row method shows that, well, you don't have to just write down the product of all the primes up through y. You can do quite a lot less work. How much less can we do? Well, historically, the first attempt to do better was the p minus 1 method. Here, you can just write down, as I say on the slide, S1 is 2 to the power e of z. What is e of z? It's a least common multiple of the integers from 1 through z. So take all prime powers less than or equal to z, multiply them, well, multiply the biggest power of each prime less than or equal to z, multiply all those together, and then form 2 to the e of z minus 1. I'll call that S1. So this is a substitute for the s in the row method. This is another number that I claim has lots of primes dividing it. The reason for that is, well, which primes divide 2 to the e of z minus 1? That's the primes for which 2 has order dividing e of z in the multiplicative group mod p. So if, in particular, p minus 1, the order of the group, is a divisor of e of z, a divisor of the least common multiple of a lot of numbers, that's a pretty good chance, depending how big z is, then p is guaranteed to be a divisor of S1. You can change this in lots of ways. There's a so-called stage 2 where you take this 2 to the e of z minus 1 and then multiply it by 2 to the e of z q minus 1, where q is multiplied by that for all the primes q from z up to, say, 10z or 100z, or z log z is what I wrote down here. You can also take bigger powers of primes, and maybe that helps. As an example of this, suppose we take z equals 20. I mean, as an example of the general method. I'm not going to say more about the tweaks to it. For the general method, suppose you write down e of z, the least common multiple of 1 through 20. That's 2 to the 4th, 16 times 9 times 5 times 7, 11, 13, etc. So that's a number with, what, 9 digits? 232, 792, 560. You can compute 2 to the e of z. Well, no, you don't want to do that. It's a gigantic number. But if you just want to compute it mod c, that's an easy computation. You can do that with, I wrote at the bottom, 34 multiplications. Not sure if that's optimal, and actually I did that by hand, so probably somebody can improve that on the computer. There's some number. I'll talk more about that in a moment. If you actually write down 2 to the power 232792560 mod p, where p is a prime in the list there, you'll get 1. 2 to the e of z is 1, mod 3 and mod 5 and mod 7 and 11. What's the first prime that's not in this list? 2. What's the next prime that's not missing? 47, yeah. 47 minus 1 is 2 times 23. So the order of 2 in the multiplicative group mod 47 is either 1 or 2 or 23 or 46. And, well, if 2 had order dividing e of z, then it couldn't have a 23 in it. It would have to have order 1 or 2, which is clearly not the case. That's why 47 doesn't show up here. Well, okay, so this is a number you can write down, which does have lots of primes. Depending on the smoothness of p minus 1, that'll tell you roughly whether p divides this S1. All right, as z grows, the number of multiplications to do this computation of 2 to the e of z, the number of squarings basically, mostly squarings, start from 2 and square and square and square and occasionally multiply by another 2. The number of squarings you need is something like 1.44 times z. That's another number you might recognize. That's just the log base 2 of e. If you choose a particular z, the 34 multiplications, I didn't say, a lot of those multiplications are just times 2, so they're very easy. Anyway, you do those multiplications very quickly for any particular c, do all the powers of 2 mod c. If z is not very big, then this is not a hard computation. And it will find lots of primes p. All the primes p are guaranteed to divide this S1 if p minus 1 divides e of z, which is about the same as saying p minus 1 is z smooth. Not exactly, because p minus 1 might have a power of 2 bigger than z or a power of 3 bigger than z, but it's unlikely. Most smooth numbers, I say without having calculated probabilities, most smooth numbers, most z smooth numbers are divisors of e of z. If you choose z in the same sub-exponential way that we're used to from last time as a function of y itself having been chosen as some sub-exponential function, if you choose z in this way, then remember the point of this e to the square root of 1/2 log thing. If you have a number up to y, its chance of being z smooth is about 1 over z. Well, that's for a uniform random integer, and p minus 1 is not a uniform random integer, p being prime, but it's kind of like uniform random integer. Actually, it seems like it should be even more smooth than uniform random integer because, hey, p minus 1 is divisible by 2. This is something where people have done lots of calculations, and the heuristics are, as always in this subject, completely accurate. You can see for a particular z, like e to the square root of 1/2 log y, that yes, there's about a 1 over z chance of p minus 1 being z smooth, and about a 1 over z chance of it dividing e of z. So this method will find a lot of primes. The compute S1 mod c, take its greatest common divisor with c, that will find a lot of primes, ones where p minus 1 is smooth. It's something like y over z, y over log y, number of primes, divided by z. 1 out of every z prime is going to be found by this method with z multiplications. You might think of the cost-effectiveness ratio there as something like z squared. You need z squared operations to find all primes. But no, it doesn't work that way, because if you don't find a prime, if p minus 1 is not z smooth, then you're not going to find it by this method. So what do you do to find other primes? How can we write down a number that's a multiple of more of the primes, up to y, with similar kind of effort? Again, this is inspirational because z is so small. Z squared is still small. Sub-exponential growth as a function of y, instead of y to the 1/2 from the row method, or y to the 1 from trial division. But this only finds some of the primes. So here's the next thing you might try, is the p plus 1 method. This writes down a sequence, instead of just powers of 2 minus 1, instead of just doubling the previous number and adding 1 to it, is maybe a stupid description of powers of 2 minus 1. Here's a different recurrence. V0 is 2, V1 is 10, V sub 2i is Vi squared minus 2, and V2i plus 1 is Vi times Vi plus 1 minus V1, V1 being 10. And then S2, our next number, which I claim is divisible by lots of little primes, is take the same E of z as before, the least common multiple of 1 through z, and then take that index in this sequence, which you can compute recursively looking at only a logarithmic number of indices, compute that minus 2. This, again, is a computation you can do mod C. The reason for these formulas, the polynomials vi squared minus 2 and vi plus 1 minus v1, is that this gives you the trace of powers of alpha in the ring z adjoint alpha mod alpha squared minus 10 alpha plus 1. What does that have to do with p plus 1, and why should we expect this v sub something minus 2 to be divisible by a prime? Well, suppose that you have this polynomial alpha squared minus 10 alpha plus 1 being irreducible mod a prime p. And suppose you have p plus 1 being a divisor of e of z, basically p plus 1 being z smooth. Then inside the field, fp adjoint alpha mod this same polynomial, alpha squared minus 10 alpha plus 1, alpha has norm 1, so its p plus first power is 1. And that means that its e of z power is 1. And therefore v sub I is 2. If you subtract 2 from v sub I, then you get 0 in fp. In other words, if p satisfies these conditions, 50-50 chance of being non-square. If it's square, then you get a product of degree 1 fields, and then you're back to the p minus 1 situation. But for half the primes, if p plus 1 is smooth, then p will be a divisor of this number s2. As an example of this, again, for z equals 20, if you write down this v sub same big number minus 2, then it has a whole lot of little prime divisors. And you can see numbers like 971. 971 minus 1, that does not factor into small primes, but 971 plus 1 does. Lots of 2s and 3s. All right, still doesn't find most of the primes up to y, but by going beyond the multiplicative group and the twisted multiplicative group to everybody's favorite group schemes, you can do better. You can find all primes up to y, and this is the elliptic curve method. This is maybe not exactly the usual description of the elliptic curve method, but, well, here's the elliptic curve method on one slide. You write down, pick a number a, say a equals 6, but in order to find all primes, you have to look at a lot of a's in order to find all primes efficiently. But let's just take a equals 6, then you define some polynomials, some recurrences there that I've written down. X sub 1 is 2, d sub 1 is 1, x sub 2i is, well, okay, you can read it for yourself and stick in 6 for the a. If you evaluate this recurrence, as you can do very efficiently with a logarithmic number of multiplications, you can evaluate this recurrence, the d sub I, where I is the least common multiple of 1 through z. Let's call that s sub 6. This is a replacement for S1 and S2, or a supplement for S1 and S2. This will detect different primes. This also has lots of little prime divisors. But the condition for this S sub 6 to be a multiple of p is kind of independent of the conditions for p to divide S1 or S2. I said at the bottom here, the variability of a is important for understanding this. You can just take a equals 6, but then to actually make the elliptic curve method efficient, S6 is kind of like S1 and S2. It'll find only some of the primes for z being chosen in the sub-exponential way I wrote down. But if you augment it with S10 and S14 and keep going for about z values of a, then suddenly it finds all the primes. What's going on behind these formulas is, well, xi over di is being calculated projectively as the x-coordinate of the ith multiple of the point 2,1 on a particular elliptic curve. So you have some point, some elliptic curve, which you can consider over fp, p being a prime that you're trying to find. Now, okay, it's not exactly true, at least I don't believe it's exactly true. I don't think anybody's been able to compute a counterexample. I don't think it's exactly true that this does compute the ith multiple of a point, because it can happen that both xi and di are divisible by a particular p. So xi over di doesn't make sense. But if di is non-zero, then it's true that xi over di is the x-coordinate of the ith multiple of that particular point 2,1 on that particular elliptic curve that I wrote down. And you can easily prove that. Well, okay, maybe it isn't so easy. Even from the usual elliptic curve formulas, you need a little extra work, with which Peter Montgomery did in '87. But okay, just a little computer verification with Macaulay shows you that this is an elliptic curve point multiplication. All right, so assuming, I've written down here, assuming that p doesn't divide di, and assuming it doesn't divide a squared minus 4 and 4a plus 10 for that curve to actually be an elliptic curve. Assuming that p is not some small divisor of 6 squared minus 4 times 6 plus 10. If you have I such that it's a multiple of the order of 2 comma 1, for instance, if E of z is a multiple of that order, for instance, if E of z is a multiple of the group order, then by the previous statement, xi over di can't be the, di can't be non-zero. If it were non-zero, then you can't have, what am I trying to say? If I is a multiple of the order, then the x-coordinate is infinity. That means di is 0. In other words, SA is a multiple of p. By Hasse, the order of the elliptic curve group is always very close to p plus 1. It varies kind of randomly with A. To prove something there, you need theorems of Doering and Lenstra. But, well, as A varies, the order is kind of unpredictable, somewhere between p plus 1 minus 2 root p and p plus 1 2 root p. And important points are it's kind of close to p, just like p minus 1 and p plus 1. It's on the scale of p, about the same chance of smoothness. But it varies with A. If you try A equals 6 and A equals 10 and different A's, then you get different numbers close to p, kind of random numbers, each with its own chance of being smooth. All right, suppose you look at z choices of A. And for each choice of A, for each elliptic curve, look at z, the least common multiple of 1 through z, call that E of z. So do about z, or 1.44 times z multiplications, well, sorry, an elliptic curve point multiplication of that number of bits. Then multiply together all the SAs you get, S6 times S10, and, well, you can also stick in times S1 and S2. What's the chance that that succeeds in finding a prime? Well, as z grows, actually, when z is chosen in the same sub-exponential way, as far as we can tell, this does get every prime. Now, this is not something the analytic number theorists can quite prove for us yet, but it's amply confirmed by experiments that every prime less than or equal to y is discovered by a choice of z elliptic curves doing about z operations on each elliptic curve. If you compute SA mod a given c that you're trying to detect smoothness of, it takes about 12z squared, 11.5z squared multiplications mod c, and that's something sub-exponential in y, instead of y to the 1/2 that we had from the Roman. If you have y squared congruences to test for smoothness, and you feed each one to the elliptic curve method, then your total time is y to the 2 plus a little o of 1. It's y squared times this sub-exponential function. All right, you can still do better. The e to the square root of 2 should look more like e to the square root of 1/2 in the actual runtime if you use what are called early aborts. I've given a simple picture here showing just one early abort, just one of what's sometimes called a large prime. But in order to really optimize early aborts, you need multiple early aborts. Let me start with the simple picture. It is not true that we want to find all of the smooth numbers among our congruences. What we want to do is find enough smooth numbers. And that's a different problem because we have as many congruences as we want. We can write down more and more I times n plus i's, or the improved sublattice I times n plus i's over q. We have a practically unlimited supply of small numbers that we would like to have being smooth. And out of those, we want to have more than y over log y, smooth numbers. So it's not true that we just write down y squared and we need to find all the smooth ones there. We can throw away some numbers that are not so likely to be smooth. An early abort works like, okay, you start with your infinite supply of congruences, and then you select, okay, we're going to take the smallest congruences, the smallest I times n plus i's. That's why I took small values of i's, because, well, that maximizes the chance that I times n plus I is smooth. And now without an early abort, the picture would say, okay, now try using the elliptic curve method to find all the primes less than or equal to y, and then see whether your unfactored piece is equal to 1. In other words, see whether your congruence is smooth. Well, in the middle here, there's another step of try trial division or the elliptic curve method, whatever method you have in mind, to factor up through y to the 1/2. And then before you keep going, before you look for primes up to y, say, wait a minute, we've got some information at this point. If we haven't found any primes or many primes up to y to the 1/2, then there's not so much chance that this number is going to be smooth. After doing some trial division or some row or some elliptic curve method up to y to the 1/2, you do an early abort where you say, okay, we're not going to bother looking at this number further if it's big. So you take all of the y squared or y cubed, however many numbers, however many congruences you started with, take the smallest ones out of the infinite supply, try trial division on, or whatever method, on all of them up to y to the 1/2, and then just keep the smallest unfactored parts. Keep the congruences that have done the best job after that trial division. Instead of just saying at the beginning we're going to look for the smallest congruences, think about that again in the middle of your smoothness detection. And then with the relatively small set of congruences that you have left, you can afford to spend more time doing some more trial division or some more elliptic curve method or whatever method. Let me concretely say that we are using trial division just to illustrate the speed up from this. Suppose that we're trial dividing up through y to the 1/2 and later trial dividing up through y, then the time for those is, of course, y to the 1/2 for trial division, the first trial division, and y for the second trial division, ignoring epsilons in the exponent. In order to balance those steps, in order to make the total time here look like y to the 1/2 per congruence, you can choose the early abort cutoff so that you keep only about 1 out of every square root of y congruences. Instead of keeping all of them and spending time y for each one, you spend time y to the 1/2 before the abort, and then you keep the best 1%, 0.1%, well, 1 over square root of y of the congruences, and that drops the time to spend, if you're spending time y on what's left, it drops, keeping only a fraction 1 over square root of y there, drops the total time down to square root of y on average per congruence. Now, a smooth number has a better chance of getting past that abort than a random number does. If you have, well, okay, I said a congruence here, that gets beyond what we can prove, but a uniform random integer, this is not supposed to be an obvious statement. The 1/4 there, that's an analysis by Pomerantz, that if you have a smooth number, then it has a substantially larger chance. Intuitively, this should make sense, but the y to the 1/4, the fact that it's that exponential is what you have to do some analysis for. A smooth number has a substantially better chance of passing an early abort than a random number does, a uniform random number. So putting together that y to the, we keep only 1 out of every y to the 1/2 numbers, and we get 1 out of every y to the 1/4 smooth numbers, we get an overall price performance improvement of a factor of y to the 1/4. Instead of spending time y per number to trial divide up through y, we spend time y to the 1/2 per number, and we find not all of the smooths, but we only lose y to the 1/4 of the smooths for a gain in time of y to the 1/2. So overall, it's a y to the 1/4 improvement. Again, to really optimize this, you need not just one early abort, but a bunch of early aborts. You can abort at, for instance, y to the 1/5 and y to the 2/5, y to the 3/5, y to the 4/5, choosing different methods, if you like, between each of those aborts to find the primes up through what, say, y to the 1/5. And, well, the same analysis tells you that there's about a 1/2 ratio in the exponent between the gain in time and the loss in the chance of a smooth number passing your early aborts. So I've written down here, if you trial divide, say, up to y to the 1/k, and then keep only a fraction 1 out of y to the 1/k, keep the best 1 out of y to the 1/k congruences as they look after you divide out the primes up through y to the 1/k, and then trial divide up to y to the 2/k, you can afford doing that, and then similarly keep only the best 1 out of every y to the 1/k. It reduces the trial division time per number from something like y to something like y to the 1/5 or y to the 1/k. The number of smooth integers that get past that, not an obvious fact, but it's true, is that the number of smooth numbers that pass that is something like y to the 1/2 of 1 minus 1/k. 1/2 of 1/k. If you divide and you look at the price performance ratio, it's y to the 1 minus 1/k over 2. If you let k slowly grow with your problem size, slowly grow with y, then this makes trial division look something like as good as the row method. It makes row look even better. From a square root of y method down to a fourth root of y, it makes the elliptic curve method look better. Again, the asymptotics, which nobody's actually worked out, but I believe it improves the e to the square root of 2 log y log log y for the time for the elliptic curve method per number down to e to the square root of 1/2 log y log log y. All of this is from the analysis by Pomerantz, although that predates ECM. Somehow this has escaped the attention of most of the people actually saying how fast factorization algorithms are. What people do in practice is something like do some sieving up to y to 1/2 maybe, and then some elliptic curve method up to y maybe, with the parameters being not carefully optimized. The project, as those of you who are in my project know, is to try to actually do better. Try to find, okay, what is the best method of doing smoothness detection? And it's clear that the answer is some grand unification of all of the methods that I've described. Maybe row doesn't have a place, but certainly trial division is the best way to find really small primes. Sieving or remainder trees, depending whether your numbers are sievable, are good for finding kind of bigger primes. The elliptic curve method is really good for finding the biggest primes. To get the best price-performance ratio, you should combine all of these with abort. Okay, I believe I have a few minutes left, and I've got a couple slides on a different perspective on these methods of finding small factors. I've been distinguishing between large primes and small primes. I said the Q-sieve is trying to find large primes and numbers. The elliptic curve method and all these other methods for today are trying to find small factors and numbers. But if you look at the speed of the elliptic curve method, it actually scales so well with the small prime bound that you could try applying it, not to congruences you get in the Q-sieve, just try applying it directly to your original number. Say you have a 512-bit n that you want to factor. Can the elliptic curve method succeed at factoring that? Well, okay, worst case is that that number, 512-bit number, is a product of a couple of 256-bit primes. And how long does it take for the elliptic curve method if y is about 2 to the 256? How many multiplications does the elliptic curve method need? Well, work out z being e to the square root of 1/2 log y log log y, and then take z squared, 12 times z squared is the number of multiplications mod n of the elliptic curve method. And again, there's lots of tweaks, so you can try to add, for instance, stage 2 to the elliptic curve method, but asymptotically it looks something like e to the square root of 2 log y log log y for the elliptic curve method to find all the primes up to y, and in particular to factor, if y is square root of n, to factor any number n. If y is square root of n, then 2 log y is 1 log n, and the little of 1 takes care of any swap here. The time for the elliptic curve method to factor n is e to the square root of log n log log n. Allowing the little of 1 in the exponents, it's roughly e to the square root log n, and assuming lots of conjectures that we can't prove. But nevertheless, this is the behavior observed in practice. Now, I said last time the Q-sieve has performance something like e to the square root of 2 log n log log n. That's the number of congruences you need to look at. So that's slower than the elliptic curve method. And it uses a lot more memory. The Q-sieve is really stupid compared to the elliptic curve method. Instead of writing down s squared minus t squared, so factoring them into s minus t, s plus t, instead of trying to find random combinations of squares and hoping you'll have a prime in common with the number you're trying to factor, this n, you can just write down a product of all the primes up through to the 256 implicitly by writing down all these elliptic curve denominators, the d sub i's, and multiplying them together, mod n. Compared to the quadratic sieve, well, all right, the quadratic sieve and the number field sieve breathe new life into those s squared minus t squared methods. The quadratic sieve is kind of comparable to the elliptic curve method. It works with smaller numbers than the elliptic curve method. It seems to have a slightly better little of 1, but it uses a lot more memory. So actually, if you wanted to factor a 512-bit number, I would recommend that you use the elliptic curve method rather than the quadratic sieve. The number field sieve takes another step up. The number field sieve is clearly asymptotically, conjecturally, roughly, well, clearly asymptotically, conjecturally better than the elliptic curve method. It has, instead of an e to the square root of log n, an e to the cube root of 2 log n, roughly. And, well, once n is sufficiently large, then the number field sieve, despite having to use lots of memory, is certainly better than the elliptic curve method. despite that, it's surprising how big the primes are that have been found by the elliptic curve method. If you just think of it as a method of finding really small primes, then hearing that an elliptic curve computation found some prime, let's see, to the 219, that's a lot of bits compared to just a few years ago that a 512-bit number was, a general 512-bit number was successfully factored by sieving methods. Well, the elliptic curve, that means primes around 2 to the 256 were found by sieving methods. And here we have, in a fairly small number of machine cycles, 10 to the 12th opteron cycles, here we have the elliptic curve method finding a prime about 2 to the 219. It's not that much smaller than 2 to the 256. The elliptic curve method, with enough computer power, would have been able to find 256-bit primes in the same time frame that they were found by sieving methods. This particular computation is perhaps misleading because the average time to find a 219-bit prime is somewhat more than this number of cycles. This particular one, it just got lucky. The first few curves, I don't know the exact number, but for a prime around 2 to the 219, you expect the number of cycles to be somewhat more than this. On the other hand, well, hey, they did get lucky. If you throw enough computer power at the elliptic curve method, then it can find surprisingly large primes. Nevertheless, the number field sieve for sufficiently large numbers is faster. In my next talk, I will tell you how the number field sieve works, how it writes down such small congruences that we can expect to find combinations of those congruences being squares using the elliptic curve method to figure out which congruences are smooth, how we can expect to do all that faster than the elliptic curve method could possibly factor a big number. Thank you for your attention.